Alright guys, so welcome to another lecture on radicals, chapter 7 on radicals. We keep moving to section 7.3, which is simplifying radical expression. So what we have done on the previous two sections was to define um, what a square root is, what a cube root is, what an n root is, and do some evaluations of radicals as functions. And then we were looking at different properties of radical expressions to play back and forth between radical form and rational exponent notation. Today, in this video, we are going to learn how to simplify radical expression using the product rule and the quotient rule, right? So let's begin with the product rule, right? So for the product rule, every time we have two radicals multiplying together, right? We have this radical times that radical. We can write them inside, we write the two radicals as one single radical and the product of the quantities inside each radical. The thing is, notice something important here. This n right here, let me do it here, and the index must be the same, right? This n and that n. All right, if they are different, well, then we cannot, or we may not. In some cases we may, but in some other cases we may. Okay, let's look at a few examples, right? Let's start with easy examples, simple examples, and then we're going to move to harder examples, to more bigger examples. All right, so in this case, notice when we don't have any number here where the radical symbol is, well, then it is assumed that we have a square root. All right, so in this case, the product of two radicals, right, is the same as the radical of the product 3 times 5. Okay. Inside of the parentheses, we may multiply the numbers, right? 3 times 5, which is 15. And if possible, simplify, right? So in this case, well, 15 is not a perfect square, right? There's no number whose square is a number 15, unless it were the number 16 or the number 9 or 25, a perfect square. Well, in that case, we can simplify, but not in this case, okay? Let's do another example. So we have the square root of 21 times the square root of x. Okay, so we have two radicals multiplying together. We can write it as the radical of the product, right? 21x, right? So simply 21x. There's nothing really to simplify other than just cleaning up the multiplication point, right? That's all I'm doing here, okay? What about the next one? Well, letter C. For letter C, notice we have the same index, right? If they are both cube roots. So we can write this as a product inside of the parentheses, 4 times 2. What are we going to get when we multiply 4 times 2? We're going to get the number 8, all right? But in this case, the number 8, it's a perfect cube, right? Because there is a number whose cube, right, whose third power equals 8, right? In this case, that number is 2. Okay. Let's move on to the next one. Okay, so we have the 4 root of 5y squared times the 4 root of 2x cubed. So in this case, we have two radicals with the same index. That means we can write everything inside of a single radical. That is the quantity 5y squared times 2x cubed. All right. So let's try to simplify the inside of the parentheses, right? So in this case, we may multiply the coefficients 5 times 2, which is going to give us a 10. So 10 times, well, let's write this in alphabetic order, x cubed times y squared, right? Now, let's look at each of the factors. The number 10 is not a perfect 4. In other words, there is no number whose fourth power equals 10, right? Now, in this case, we cannot simplify the x's any further or the y's any further because we cannot, if we write this x, we would get x to the 3/4, right? So we don't get an integer here as we would on other examples that we're going to do next, right? So for now, let's just, this is the final answer for this exercise. Okay, let's look at the next one. Now we have fractions inside, right? How are we going to treat this? Well, the same way. So the square root of the quantity 2 divided by a times b divided by 3. Okay, what do we do when we multiply fractions together? Just multiply across. Multiply 2 times b and a times 3. In the numerator, we get 2b, and in the denominator, a 3a. Okay, and that's final answer for us. There's nothing else to simplify because we cannot divide 2 by 3 or b over a. Well, that's just b over a. There is no common factors to divide out. All right, now we're going to do this multiplication but backwards, right? So how do we simplify this? Well, okay. So in the previous section, right, in the previous couple sections, we were evaluating quantities like the square root of 25, which equals 5, or the cube root of 27, which equals 3, or the fifth root of 32, which equals 2, right? We were looking at perfect nth powers, right? Like in the first case, perfect square roots, perfect cube roots, and perfect fifth roots, right? Now, can we have expressions with numbers that do not have perfect roots, perfect square root, perfect cube root, perfect fifth root? The answer to the question is yes. And we are going to look at some examples right here. Okay, observe the first one, letter A. The square root of 50. Okay, can you think of a number whose square equals 50? No, right? Unfortunately not. We were close, right, to a number whose square is a perfect, that is a perfect square. For example, 49, right? 49, the square root of 49 is 7, right? But in this case, this is not 49. This is a different number, right? So what are we going to do? The steps to do this is number 1, determine the largest perfect nth power factor of the radicand. All right, largest perfect nth power factor. Okay, that's like a lot of words, right? Let's see. So we're going to look for the largest perfect squared, or the largest perfect cubed, or the largest perfect fourth, or the largest perfect fifth, the largest perfect sixth, etc. All right. Now, what are we going to do here? Okay, so we are going to factor the number 50, okay, in a way that one of the factors is a perfect, okay, we're looking for perfect squares here. How do we know we're looking for a perfect square? Because of the index right here, right? Then the absence of a number in there, right, means a 2. So we're looking for a perfect square. Okay, the question is, can we write this in a way that one of the factors is a perfect square? Yes. It turns out that the square of 50, right, is the same as the square root of 25 times 2. All right. Now, from now on, I'm going to highlight with green the perfect squares, and with purple, the numbers that are not perfect squares, or green with perfect cubes, and purple the ones that are not perfect cubes, or green perfect fours, and purple the ones that are not perfect four, and so on, right? Now, what are we going to do next? We are going to do the backwards property, right? Let me recall the property. The property says and root of a times and root of b equals and root of a times b. So on the exercises, on the previous pages, we were looking at this property, looking at this way, right? Now we're going to do it backwards. We have a product up to numbers 25 and 2. We are going to break it up into the product of two radicals this time. All right. So I'm going to write the square root of 25 times the square root of 2. Okay. I will keep highlighting all this. This is a perfect square. This one we can evaluate, right? Square root of 25 is going to be 5. However, the purple one is the square root of 2, so that's not going to be possible to write it there's no way we can take the square root of 2 and get an exact number, right? So we only take care of the square root of 25, which is 5 times the square root of 2. Okay, and that's final answer for this first exercise. Okay, let's look at another example. We're going to do a bunch, by the way. So in this case, what are we going to do? We are going to look for, again, perfect squares. Notice B and C are going to be similar, right? They have the same number, 24 and 24. However, on example B, we're looking for the square root, but for letter C, we're looking for the cube root. We will see the differences. All right, so we were looking for a factor of 24, right? We're going to factor the number 24, for example, 2 times 12, right? But is that going to work? Let's see. 12 times 2. We need to break it apart in a way that one of the factors is a perfect square. However, in this case, 12 is not a perfect square, and so is not the number 2. So this is not going to work. We need to find another way to simplify this. Okay. How about 8 times 2? Well, I mean 3. 8 times 3, right? 8 is not a perfect square, and so is not the number 3. So this is not going to work either, right? So we need to try another way, right? There is another way to simplify this. How about 4 times 6? And that seems like it's going to work. Why? Because here we have a perfect square, the number 4, but 6 is not a perfect square, which I will highlight with purple. Okay, so let's simplify this as the product of two radicals, 4 times the square root of 4 times the square root of 6. All right, so let's highlight the one. Let's keep highlighting with the same colors. Green for the ones that are good, right? For evaluating the square root, and purple for the ones that won't. Okay, so this is going to be the square root of 4. It's going to be 2 and times the square root of 6. Okay, and that's all we do. That's about it. All right, let's move on to letter C. Okay, so in this case, it's very similar to letter C. However, look at this little index right here. The one I just highlighted with orange, right? The index is 3. So this time we're looking for perfect cubes, right? That's what we're looking for this time, a perfect cube. All right. Okay. So we already tried 4 times 6. That's not as we tried. Okay, let's try 4 times 6. 4 times 6 is not going to work because none of them, 4 or 6, are perfect cubes. In other words, there's no number whose cubed is 4, or there's no number whose cubed is 6, so we need to try another way. Okay, so let's erase for n6. Let's erase for n6. How about, well, we look at 12 times 2 earlier, right? 12 times 2, 12 times 2. But again, in this case, there's no way to look for a number whose cubed is 12 or a number whose cube is 2, so we need to find another way. Okay, the other way is the one that we already looked as well, 8 times 3, all right? In this case, guys, check this out. 8 is a perfect cube, right? 2 times 2 times 2. 2 multiplied 3 times is going to give us 8. However, the number 3 is not. So let's highlight it. Now, let's write another radical. Okay, let's break it up, rather break it up into the product of two radicals. The cube root of 8 times the cube root of 3. Right? Okay, so let me highlight the perfect cube, the one that we can evaluate, and I'm going to highlight with pink, or purple rather, the one that we cannot evaluate. Okay, so the cube root of 8 is 2, and that times the cube root of 2. Okay, final answer. All right, letter D. I like this example, letter D, because when I give this in the class, I typically leave all the students to work on their own. Actually, if you want to pause the video and would you like to try it on your own, go ahead and do it. All right, pause the video and then keep going. Okay, I'm gonna do it now. Okay, why do I like this example? Because, well, the square root of 72. Okay, I'm gonna do it on this side. Okay, so let me use a different color actually, so I can make distinction about it. Okay, so the square root of 72. This is a very curious exercise because, number one, students give me this as a final answer, 9 times 8, right? They also give me what other number? I believe 4 times 18, right? And then other one I've seen as well is 36 times 2. And it turns out that the three of them are, in a way, they are correct. I mean, they're, in a way, in the right path, right? Right, because this is a perfect square, this is a perfect square, and this is also a perfect square, right? Again, keep in mind that this is an invisible 2 here that we don't need to write, right? But it should be understood that we are looking at square roots. So the three of these are correct. Which one do we go? Okay, let us go back a little bit to the definition, right? Let us go back to the definition, and we'll look for the largest perfect nth power, right? The largest perfect nth power. Although the three versions here are correct, all right, the best choice is this one because, well, this is a perfect square, 9 and 4, but none of these are the highest or the largest perfect square. Unlike 36, this is the largest one. All right, so we're going to take this one. Okay, so let's see. We're going to write this as the square root of 36 times 2. Okay, in this case, 36 is the perfect square. 2 is not a perfect square. So let's break this up into the square root of 36 times the square root of 2. Okay, let's keep going with the highlighters, and to denote which one is the perfect square and which one is not, and evaluate the one that is the perfect square. So 6 times root of 2. Okay, final answer. Okay, what happens if we do this one? Okay, if we do this one, you would do the square root of 9, right, times the square root of 8, right? This is fine, right? This is going to be 3 square root of 8. And this looks like the final answer. The problem is, if you put this as a final answer on MyMATLAB, they are going to tell you, although your answer is correct, blah, 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 yada, 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 it's not written in the simplest form. Yeah, yes. Okay, you know, MathXL is very picky about this. So you need to keep working on this one. This is the same as saying 3 times the square root of 4 times 2. 3 times square root of 4 times the square root of 2. 3 times 2 times the square root of 2. Multiply these two, we get 6 root of 2, right? The same answer as we got. But do you see all the steps that it takes to get to this answer? They are unnecessary. That's why, guys, that's why we go with the largest, right? We go with the largest of, in this case, the perfect square. We could run into a situation like this, but with perfect cubes, in which there's different ways to factor out a number, but we don't, one of the factors is, yes, a perfect cube, but not the highest. And in that case, try to go with the highest. So you do you simplify this exercise in 1, 2 steps, right? Instead of 1, right? So in this case, notice how we did only 1 and 2 steps, right? That's all it took. In this case, it took 1, 2, 3, 4, 5 steps. 5 steps to solve the exact same problem, right? So again, try to keep it as simple as possible. So, I mean, sometimes it takes a little thinking, right? But again, you have a calculator, right? You have a calculator to play with the numbers to determine whether it's divisible by 2, by 4, by 9, and get the largest number possible, right? Okay, let's move on to the next example, letter E. All right, letter E, the square root of 25 times x cubed. Okay, what about it? Okay, so right off the bat, you may notice the number 25 right here is a perfect square, and you may want to evaluate it, right? That's fine, no problem. However, let me walk you through this one, and so I can show you how to do a good organization of factors that are perfect, in this case, perfect squares, right? Or perfect cubes, or perfect fours, or etc., right? In this case, let's do one with perfect squares. So this is the same as saying 25 times, okay, in this case, notice x cubed is not a perfect square. Okay, let me go back a little bit to what we learned in the previous sections. Okay, if you want to use the back side of the page, right, or your notes below if you're just writing on your notebook, okay, you might want to recall the following. On the previous section, we learned that the square root, well, actually the nth root of a to the n power, right, is equal to a to the n divided by n, right? In other words, the index, the number n, which corresponds to the index, should divide, or well, may divide the exponent of the variable inside of the radical, right? For example, let's see. How about the square root of x to the 4th power, right? Okay, this is the same as saying x to the 4 divided by 2, and if we divide 4 by 2, we get x squared, right? If we have the square root of n, no, let's not use n to avoid confusions. How about r to the 8th power, right? So in this case, we divide, so we write r to the 8 divided by 2, and this divides to 4, okay? So all we're doing, notice, these are numbers that are divisible, and we get as a final answer a perfect integer, right? So for example, if we do the cube root of x to the 12, right, only divide 12 by 3 and we get 4. How come? Because x to the 12 divided by 3, that's x to the 4th power, right? I don't know, let me do 5. X to the 15, right? Divide 15 by 5, x to the 15 over 5, and that's x to the 3rd power. Or the 7th root of x to the 49, why not? Right? Same, divide 49 by 7, we get 7. Okay, let me write it down. So hopefully after practicing with a bunch of this, right, you can do that in your head, maybe, or maybe not. If you don't feel confident about it, write this intermediate step before you write down the final answer, right? So, I don't know, let's see. Let me do another one. How about the 6th root of a to the 36, right? This is a to the 36 divided by 6, which is simply a to the 6, right? So all we do is divide these two numbers. Divide the exponent by the index, right? And get a perfect integer, right? However, over here, when we try to divide, okay, we're trying to divide 3 by 2. In this case, 3 divided by 2 doesn't give us an integer. So in this case, what do? We are going to break it up into x to the 2nd power times x, right? Because, well, this will leave us with an invisible 1. And 2 plus 1, because when we multiply the same bases, we add the exponents. 2 plus 1 equals 3. All right? Now, from here, we are going to highlight the perfect squares. 25 is a perfect square, and so is x squared. However, x to the 1st power is not a perfect square, right? So, I'm going to break this up into 2 radicals, right? The first radical that contains the ones in green, the ones that are the perfect squares. And on the second radical, the one that contains the ones that are not perfect squares, right? And I keep the highlighting, right, with the corresponding color, just so you can see, you can keep track of the ones that are perfect squares and the ones that are not perfect squares. Now let's evaluate this. Okay, square root of 25, that's 5. Square root of x squared, x, times square root of x. And that's how we simplify this one. Okay, let's do another example, one with cube roots, right? So now we are going to look for perfect cubes. Okay, notice on the previous example, because of this index right here, square root, we were looking for perfect squares, right? Now we have a cube root, we look for perfect cubes. Okay, now, well, when it comes to moving to higher indices like the cube root, the 4 root, well, it's not as easy as working with perfect squares, right? Because perfect squares are relatively easy to memorize, right? To keep in mind. Well, the first few perfect squares, for example, we have number 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169. Well, that's enough, right? However, when it comes to perfect cubes, they are not the most common numbers, right? So let's list the first few. Okay, so 1 cubed, I'm going to list them on the left side here. Okay, I'm going to list them here. 1 cubed equals 1, 2 cubed equals 8, 3 cubed equals 27, 4 cubed 64. Okay, 5 cubed equals 125. Okay, now notice this. Notice this 54 right here. This 54 should be between 27 and 64, right? So let's see, let's try to factor the number 54 in a way that one of the factors is a perfect cube, because it is clear that the number 54 is not a perfect cube because there's no integer whose third power equals 54. Okay, so let's try. Notice the number 54 is an even number. Let's try dividing by 2. Okay, so 54 divided by 2, if we divide, you might want to use your calculator. That's fine. That's 27 times 2. All right, that's 27 times 2. Now, between 27 and 2, is any of them a perfect cube? The answer to this question is yes. Okay, 27, it's a perfect cube. That's 3 cubed. That's the one right here, right? Okay, let me erase this. So I'm going to rewrite this as the cube root of, okay, instead of the number 54, all right, I'm going to write it as 27 times 2. Okay, so for the numbers, we need to break it up into factors in a way that at least one of the factors is a perfect nth power, or like in this case, a perfect cube. Now, what about the variable factors? Okay, x to the 6. All we need to know is whether this number 6 is divisible by 3, by the index, which is what I did on the side of the screen a few minutes ago, right? So in this case, it turns out that 6 is divisible by 3, so x to the 6th is a perfect cube. So let's just leave it as x to the 6th power. All right. I'm worried about y to the 8th power. So for y to the 8th power, okay, observe the power, it's a number 8. Okay, let me write down the power below 8. The question is 8 divisible by 3? And does that give us an integer as an answer? The answer is no, okay? So this one fails to be divided by 3. What about one integer below? One integer below 8 will be the number 7. Okay, the question is 7 divisible by 3? And again, the answer is no, right? So cross it out. Okay, cross it out. Okay, what about one integer below 7? How about the number 6? Okay, is 6 divisible by 3? And in this case, the answer is yes. It's just exactly as on the previous factor, the one corresponding to x. So I'm going to write y to the 8 as y to the 6 times y squared, right? Because 6 plus 2 equals the 8 right here, right? That's going to give us back those two numbers. And we are done factoring everything, right? Okay, let's highlight with green all the perfect cubes, right? We're looking for perfect cubes. Let's highlight the perfect cubes. 27, x to the 6th, y to the 6th. With purple, we are going to highlight the ones that are not perfect cubes. Okay, so I'm going to write two separate radicals. One cube root with the perfect cubes, 27, x to the 6th, y to the 6th times the cube root of 2y squared. And again, let me keep highlighting. Green for the ones that are nice, perfect cubes, and purple for the ones that are not perfect cubes. The ones that are not perfect cubes, again, we leave them alone inside of the radical, right? And we just evaluate the ones in green, okay? So the cube root of 27 is 3. The cube root of x to the 6, in other words, 6 divided by 3, that goes twice, right? So x squared, and y to the 6 over 3, that's y squared, times the cube root of 2y squared. Okay. All right. This is final answer to this. Okay. All right. Let's move on to the next example. All right. Let's number 1 determine whether, okay, look for number 1 thing we look at is always the index. That's the boss. That's what is going to tell us what to do. For example, for letter E, when we look at the index, we turn out being a square root. So we are looking for perfect squares. For letter F, the index was a 3, so we were looking for perfect cubes, all right? Now, for letter G, the index is 4, so we are looking for perfect fourths. Okay, let me write that down. And let me erase this to avoid having a lot of numbers, right? So we're looking for perfect fourths, right? That's what this index is telling us. And yes, again, I know that's it's working with power, with quantities to the 4th power. It's not a trivial procedure the way it is for squares, right? So we are going to use a calculator to determine what number to the 4th power equals 81. Okay, let's try 2. 2 times 2, okay, that's 2 squared, that's 4 times 2, that's 8 times, okay, to the 4th power, that's 16. No, we need to try a larger number. 3 squared, that's 9 times 3, 27 times 3, 81. That's the one. All right, so let's start breaking up this as, actually, this is a perfect 4. We don't need to break it up into anything, right? So this is what we do. 4th root of 81. Okay, what about the powers of z? Okay, so number 1. Does 11 is a number 11 divisible by 4, and does that give us a perfect integer? The answer, let's look at that. Okay, is 11 divisible by 4? And in this case, it doesn't work. What about one integer below? Okay, what about 10? Is the number 10 divisible by 4? And does that give us a perfect integer as an answer? The answer is, again, no. What about one integer below, 9? Can we divide 9 by 4 then? 9 over 4, do we get an integer? Nope. Don't get that either. Let's try one more. One integer below 9, how about the number 8? Is 8 divisible by 4? Yes, finally. So this is what we do. We will write z to the 8th power times z to the remaining powers that added up with 8 give us back the number 11. So in this case, 3. In other words, how many numbers did we cross here? We crossed 3 of them. That's the same as the numbers that we crossed as the remaining power, right? Okay. Now from here we are going to highlight not the perfect squares, not the perfect cubes, but in this case the perfect fourths. All right, the perfect fourths, and when we do that, we get to highlight the number 81 because that's a perfect 4 and the variable z to the 8th power. Okay, now z to the 3rd power, on the other hand, we'll leave it highlighted with purple because that's not a perfect 4. In fact, notice if we try to divide 3 by 4, it's not going to go. It's not even going to go, and it's not even going to be a single integer, right? So we leave it like this. Now let's break this up into the product of two radicals. Again, the product of the radical with the quantities in green, that is the quantities that have a perfect fourth in this case, times the radical with the quantities inside that do not have a perfect fourth root. Okay, again, keep highlighting with green, right? The ones that are perfect fourths, with purple, the ones that are not perfect fourths. Okay, now the 4 root of 81, again, we said that was 3. Now, if z to the power 8 divided by 4, okay, what do we get? We get 2 times the cube root of z cubed. Oh no, not the cube root. Hold on a second. This is supposed to be fourth root. Okay, the fourth root. And that's final answer. Okay. All right. Let's look at letter H and letter I. Letter H and letter I, they look almost the same. What's the difference? This is to look for perfect squares. And here we look for perfect cubes, as the index indicates, right? So now let's start looking at the x's. Okay, we have x to the 11, right? Notice we don't have numerical coefficients in this case, right? Only powers of x, y, and z. So is 11 divisible by 2? Okay, in this case, it's not divisible by 2, right? What about one number less? How about 10? Is 10 divisible by the index 2? The answer in this case is yes, it's going to be 5, right? Okay, so let's start breaking up x to the 10th power times x. Okay, let's go with the y's. Okay, let me make this a little bit smaller. Okay, is 17 divisible by 2? In this case, it's not going to be divisible by 2, so let's cross this out. Okay, cross out the 17. And let's try one integer less. What about 16? Is 16 divisible by the index 2? The answer is yes, because 16 divided by 2 is going to give us an integer, a nice integer, which is 2. So we write y to the 16th power times y, right? Now what about z? Okay, in this case we can notice we have a z to the 8th power, right? And 8 happens to be divisible by the index 2, so we don't need to break this one up, just the same way we did with the x's and the y's. Okay, so z to the 8th power. All right, let's highlight with green all the perfect squares, that is x to the 10th, y to the 16th, and z to the 8th. On the other hand, we highlight with purple the ones that are not perfect squares, all right? So let's write a couple of radicals, one with the factors that are perfect squares, and another radical with the factors inside of it that are not perfect squares. Okay, let me use green again to highlight the ones that are perfect square, the ones that we are permitted to keep simplifying. In this case, we are not able to simplify. All right. So now all we do is divide 10 by 2. That's going to be x to the 5th. 16 divided by 2, that's 8. And 8 divided by 2, that's 4. All right. Times square root of x, y. Okay. So that's final answer. All right. Let's look at letter I. Letter I again has the same quantity inside of the radical. However, what changes this time is the index, right? We were looking for perfect cubes as we mentioned earlier, right? Perfect cubes. Okay. So let's see. Let's look at each power. Can we divide 11 by 3 and get a perfect integer? The answer is no. All right. So 11 divided by 3, okay, which is the index, doesn't go evenly, right? So cross it out. Okay, and let's try the next one. Well, that is one integer below. What about the number 10? Is 10 divisible by 3? The answer is no. Okay, so let's cross out that possibility and try one integer below, one integer less than 10, which is 9. In this case, is 9 divisible by 3? The answer is yes. So we're good here. So let's start writing our radical expression. That's going to be x to the 9th power times x to the 2nd power, right? Okay. Now let's go with the y's. Let's start with its power, 17. Okay, the question is 17 divisible by 3? The answer to this question is no. Okay, so let's try one integer less. Okay, so cross out the 17. Let's go with one less. 16. Is 16 divisible by 3? Again, the answer to this question is no. So cross out 16. Let's try one integer less. 15. Now the question is 15 divisible by 3? Yes, in this case it goes evenly, right? So let's break this up into y to the 15 times y squared, right? That is equal to 17. We'll verify that at the end of the factorization, right? Okay, let's go with the z's now. Is the number 8, the power of z, divisible by 3? In this case, the answer is no. So let's try one integer less. That is the number 7. Okay, now let's see. Is 7 divisible by 3? The answer is no, right? So let's cross it out. Let's cross out that possibility and look at one below. That is 6. Now is 6 divisible by 3? The answer is yes, right? So we write z to the 6th power right, times z squared. Okay, notice for, okay, let me highlight, 9 plus 2 equals 11. See how that's the same? 15 plus 2, that's 17, right? And last but not least, for the powers of z, 6 plus 2, that's equals to 8, right? Now let's highlight the perfect cubes. X to the 9th, y to the 15, and z to the 6th, right? Now, and keep highlighted with pink all the factors that are not perfect cubes. So the cube root of x to the 9 times y to the, okay, that doesn't look like a 9, y to the 15, and z to the 6th times the cube root of x squared, y squared, z squared. The factors, the first ones we can evaluate, highlight them with green, and highlight with purple the ones that we cannot simplify. So 9 divided by 3, that's going to be x cubed. 15 divided by 3, that is going to be y to the 5th. And z to the 6th divided by 3, that's 2, times the cube root of x squared, y squared, z squared. Final answer. Okay, so these are examples in which we use the product rule for radicals. And now let's look at the other property, or the other rule, the quotient rule. Okay, so just the same way when we have the quotient of two radicals, right? We can write the quotient of two radicals as the radical of a single quotient, or backwards, we can simplify a big radical into two. Okay, let's do first in this direction, right? We have a big radical, and let's break it up into two separate radicals. Okay, so we are going to rewrite this as the square root of 25 divided by the square root of 49, and evaluate the corresponding root whenever possible. In this case, it turns out that 25 is a perfect square, and so 49 is. The square root of 25 is 5, the square root of 49 is 7, okay? Letter B, the square root of x divided by 9, so this is the same as saying square root of x divided by the square root of 9. Well, in this case, we don't know what x is, so we just leave it as it is, square root of x, and the square root of 9 is 3. No need to do anything else, any further. Now we're talking about cube roots, so we have the cube root of 8 divided by the cube root of 27. Okay, so they are both perfect cubes, right? The cube root of 8 is 2, and the cube root of 27 is 3. So 2/3, final answer. Letter D, we're talking about 4 roots. Same concept, same idea. 4 root of 3 in the numerator, 4th root of 16 y to the 4th in the denominator. Okay, so 3 is not a perfect 4. There's no way we can look for a number whose 4th power is 3, so just leave it like that, all right? And for the square root, the 4th root rather, of 16 divided of 16 y to the 4th, 16 happens to be a perfect 4th power, that is 2, and the power of y, which is 4, is divisible by its index evenly, so that's just going to leave us with y. All right. Okay, now let's apply this backwards. So we have the quotient of two radicals, right? One radical in the numerator, another radical in the denominator. So let's write everything inside of the same radical, right? The reason why we can do this is because this is a 2, an invisible 2, and an invisible 2. If we had, however, well, something like this, square root of 20 divided by the cube root of 5, we wouldn't be able to write it as a single radical, right? The reason why is this index is different than that index, right? And we need to have the same indices in order to apply both the product rule of radicals and the quotient rule of radicals, okay? So now what are we going to do? Well, simplify the expression inside of the radical. 20 divided by 5, that's 4. And 4 is a perfect square. Let's evaluate it. We get a 2. Final answer. All right. Let's look at letter F. So, and you might want to be careful with letter F. Notice the number 2 right here in the denominator. And the reason why you need to be careful is because my advice, write this 2 in the denominator as 1/2, right? Times the quotient of 50x and the square root of 2, right? And now we may focus on the expression that has the radicals only, right? Okay, let's go ahead and simplify that one. So this will be 1/2 times the square root of 50x divided by 2. Okay. And let's simplify. Let's focus on the expression inside of the radical. We notice we can divide 50 by 2. That's 25x. Okay. In this case, notice how 25 is a perfect square, but in this case, x is not a perfect square, right? So let's break this up into 1/2 times the square root of 25 times the square root of x. Okay, and again, highlight the perfect squares with green, highlight the non-perfect squares with purple. So this will be 1/2 the square root of 5, which is 5, times the square root of x. If we multiply 1/2 times 5, we get simply 5/2 square root of x. Or equivalently, this is the same as saying 5 square root of x divided by 2. Either one of these two is correct when it comes to inputting on MyMATLAB. Okay. Let's do a similar one now, one that has cube roots. Okay, in this case, this 7 is in the numerator. Don't worry about it, right? This is just 7 times the cube root of, okay, let me write down 48 x to the 4th power y to the 8th divided by 6 y to the 6th. Okay. Now let's simplify the expression inside of the radical. 48 divided by 6. That's going to give us 8. And then this x, notice this x to the 4. There is no other x's to simplify with. Just go x to the 4th power. Okay. And in this case, we may divide y to the 8th by y to the 6th. We do that by subtracting 6 from 8 for the exponents, and we get y squared. All right, let's see. One at a time. Is 8 a perfect square? The answer is yes. We have used that one a few times. Now the question is, for the powers of x, is 4 divisible by 3? Well, in this case, we cannot divide 4 by 3 and get a perfect integer. So we need to break this one up, right? On the other hand, is 2 divisible by 3? Well, the number 2 is smaller than 3, so we cannot do anything about it. Okay? So, this is 7 times the cube root of 8 times x cubed times x times y squared. All right? So now it's time to highlight with green all the factors that are perfect cubes, all right? And highlight with purple the factors that are not perfect cubes. And we're going to do 2 radicals, just the same way we did a couple pages ago, right? 1 radical for the perfect cubes times another radical with the non-perfect cubes. Okay, highlight the non-perfect cubes with purple, highlight the perfect cubes with green. Okay, evaluate the cube root, in this case 7 times 2, and divide 3 by 3, we get 1 for the power of x, times just the cube root of x, y squared, which is the factors that are not perfect cubes. We are only one step away to get this done. Just multiply 7 times 2 to get 14 x times the cube root of x, y squared. Final answer to this one. Okay. All right, let's do one last one before we move on to the next topic. Okay, so now we have the fourth root, exactly the same type of problem, but on the previous ones, well, let me highlight the indices. We were looking for perfect squares. Here we were looking for perfect cubes. Now on this exercise, we are going to look for perfect fours, right? Again, the first thing we look at every time we have a radical problem is the index. That's going to tell us what are we going to do throughout the exercise. Are we going to look for perfect squares? Are we going to look for perfect cubes? We're going to look for perfect fours, etc. Right? In this case, we look for perfect fours. However, first of all, we apply the property of radicals, right? The end root of a divided by the end root of b. This is the same as huge radical with root n of index n of a over b, right? And that's what we're going to do over here, okay? Let me just erase this so it doesn't confuse anyone. All right, so this is going to be the fourth root of 32, a to the 8th power, b to the 6th, divided by ab squared. Okay, so let's simplify the expression inside of the radical. So 32 is just going to be 32. And when we divide a to the 8th power by 8, we are going to get a to the 7th power. And finally, when we divide b to the 6th by b squared, we are going to get b to the 4th power. Okay, now let's close this radical. And number 1, let's start looking for perfect fours. Okay. Number 1, is the number 32 a perfect four? In other words, is there a number whose 4th power is 32? Well, in this case, the answer is no. Okay, 2 to the 2nd power is 4, then to the 3rd is 8, to the 4th is 16. No, it's not going to be, right? And to the 5th power is going to be 32. So we are going to break this number up into the 4th root of 16 times 2. Now, let's look at the power of a. Okay, 7 is the power 7 divisible by 4 is not. So, cross out that possibility. Let's do one below. 6. So, the question is 6 divisible by 4? The answer is no as well. So, cross it out. Let's do one less. 5 is 5 divisible by 4? The answer is no. Cross it out, right? And let's do one more. 4 is 4 divisible by 4? The answer is yes, right? So let's break it up into a to the 4th power times a cubed, right? Because 4 plus 3 equals 7, right? Just as I highlighted. Now let's look at b. Is the power of b, which is 4, divisible by 4? Well, yes, that goes evenly, so no need to break it up the same way we did it for a. Okay, so b to the 4th simply. Okay, let's cross the radical symbol. Now let's highlight with greens all the perfect fourths. And let's highlight with purple all the non-perfect fourths, right? Now, let's write one radical for the perfect fourths. 16a to the 4th, b to the 4th, and another radical to a cubed. Okay, so let's highlight with green all the perfect fourths, and let's highlight with purple the non-perfect fourth. Again, just so you can keep track of the ones that we can simplify and the ones that we cannot simplify any further. Okay, so what number to the 4th power equals 16? In this case, 2. When we divide the power of a, which is 4, by 4, we get 1. That's just a to the 1st power. We don't need to write that one. And same for b. Times 4 times 2a cubed. Okay, it's not looking good. Okay. All right. Let's call it a day for this example, right? So that's pretty much about it. That's as far as the properties of radicals, right? So rather the quotient rule and the product rule. Now we're going to look at a couple of applications of simplifying this, in which this type of problem comes into play, right? So the distance formula, right? Suppose you have a couple of points, right? A point x1 comma y1, right? And another point x2 comma y2. Okay, well, let me actually move this a little bit down here and this one up here, right? So if we draw a linear segment containing the points x1 and y1, we should get something like this. Okay, I'm gonna struggle here. Okay, we get this, right? So we're gonna look for this distance d, right, which is denoted right here. and we are going to subtract the differences, right, between this is x2 minus x1, right, and this vertical distance, this is y2 minus y1, right? So if you might want to call this big A and you might want to call this big B, right? We're looking, this distance, right, is generating a right triangle, right? And you might remember a powerful theorem that comes from for right triangles that relates the distances of the length of the sides and the hypotenuse, right? That is a squared plus b squared equals c squared, right? In this case is d squared, right? And then this is going to be for a squared, this is x2 minus x1 quantity squared plus y2 minus y1, which is b squared, right, equals d squared. If you take the square root on both sides, right, take the square root, we can cancel this d equals that expression, and that's no other than the formula that we have here. Okay, you don't need to write this down if you don't want. This is just a simple derivation, right? In fact, I will reserve this this picture for the example that we're going to do. Okay, so find the distance between the points 1, 2, and 5, 5. Okay, let me write down the formula here again. Okay, so we can refer to it. Well, actually, I'm going to write it on the example. So d equals the square root of x2 minus x1 squared plus y2 minus y1 quantity squared. Okay, which one is x1? Which one is x2? Which one is y1? Which one is y2? Okay, so this is P1, this is P2, right? So this will be our x1, this will be our x2. I mean, not x2. This will be our y1. This is, on the other hand, our x2 and our y2. And all we do is plug in the numbers in the formula. Okay, so d equals the square root of x2, which is 5, minus 1, which is x1, quantity squared, plus y2, which is 5 also, minus 2, and that quantity squared. Okay, let's simplify. Remember, according to PEMDAS, we simplify the quantities inside of the parentheses first, right? That has the highest hierarchy here, the highest priority. So 5 minus 1, that's going to give us 4 quantity squared. 5 minus 2, that equals 3 squared. So that's going to be 16 plus 9, which is, actually, I'm going to go here. Square root of 25. But what's the square root of 25? That's a really nice number, right? 5. Okay, what were we doing then here? All right, let's see. Let me erase all this I did. All right, let's label the point 1, 2, right, which is the first given point, and the point 5, 5. So we were looking for this distance right, from the point 1, 2 and 5, 5. Okay. So this is what we did. We found the distance, which is 5 units. All right. And these units could be centimeters, could be millimeters, could be inches, could be kilometers, right? I don't know, depending on the application, right? This is just given with numbers. Let's do another example. Okay. D equals the square root of x2 minus x1 squared plus y2 minus y1 squared, in which this is x1, right? That's going to be here. This is y1, that's going to go here. And this is x2 and y2 respectively. So 1 goes in right here and -4 goes right there. All right. So let's just plug in the numbers and simplify. D equals to the square root of x2, which is 1. Be careful here with all the parentheses that we're going to have. So this is going to be 1 minus -2, right? Quantity squared. Do you see what's going on here? The smile rule, right? Plus y2, which is -4, minus y1, which is 3. Okay? Be very, very careful here. Quantity squared. Then, okay, so 1, this is going to be 1 plus 2, right? That's going to be 3 squared plus -4 minus 3, that's going to be -7. Be careful with the signs, with the rules of signs. Okay, and 3 squared, that's a total of 9. And -7 squared, that's a positive 49. So we add these two together, 49 plus 9, that's 58. Well, in this case, this is final answer, because number 1, 58, it's not a perfect square. And if you try to factor this 58 and try to find a factor that is a perfect square, as what we did on the previous pages, well, divide this by 2. This is going to be 29. So we were going to have 2 times 29. None of these are perfect squares, right? So we're done with this problem. And we look at the last of the pages, which is another application. That's the midpoint formula. Okay, so let me just do one example. Let's find the midpoint between the points 1, 2 and 5, 5. Okay, the midpoint formula, let me write it down. Okay, it's going to be the sum of x1 plus x2 divided by 2. That is the average, if you will, right? Because notice we are adding two quantities and then dividing it by 2. That's basically finding the average. And then y2 plus, y1 plus y2. Divide that by 2. So let's just plug in the numbers. This is x1, x1, x2. Let me highlight them. Okay, so this will be 1 plus 5 divided by 2, comma, y2 plus y1 plus y2, 2 plus 5. And let's simplify. So that's going to be 1 plus 5, that's 6 divided by 2, comma, 2 plus 5, which is 7 divided by 2. In this case, we can simplify 6 divided by 2, that's 3. comma 7 halves. Okay, what is this point representing? The point 3 comma 7 halves is the point right in the middle of 1 comma 2 and 5 5. Let's verify that graphically. Okay, so let's plot the point 1 comma 2 again and the point 5 comma 5. Okay, let's draw a linear segment, right? And well, I need this to be perfect. Okay, so I'm gonna need a rule, I guess. All right, so I think that's good. Okay, so this is the point 1 comma 2 and this is the point 5 comma 5. So the midpoint, which is 3, let's use decimal, 7 divided by 2, that's 3.5, right? So the point, we go 3 comma 1 2 3.5. Oh, isn't that the point exactly in the middle between 1 comma 2 and 5 comma 5? And that's what this represents, right? Let's do one more and we call it a day for this section. So n, which is x1 plus x2 divided by 2, comma y1 plus y2 divided by 2. Okay, so let's highlight the x's, -2 and 1. Those are going to be there. And let's highlight the y's here and there. So this is going to be, okay, let me move this a little bit towards the left. And plug in the numbers only. Okay, that's -2 plus 1 divided by 2, comma 3 plus -4. Careful with signs here, as usual, then divide by 2. So -2 plus 1, what is that going to give us? That's going to be a -1/2, comma 3 plus -4. This is the same as 3 minus 4, but 3 minus 4, what is that going to be? 1/2 as well. And that's final answer. No need to graph this one, only graph one, the first one in this case, just so you can see the bigger picture of what this is about, right? And guys, this is the end of the lecture for this section 7.3, simplifying radical expressions. On the next video, we will cover section 7.4, which will be adding, subtracting, and multiplying radical expressions. I'll see you in the other video. In the meantime, bye bye, see you next time.